Nashville Systems Programming Day was sponsored by Stratasan, Advanced Analytics for Healthcare. Learn more at stratasan.com.
So all of your brains are probably bursting with knowledge now, so we'll take it a little easy. So let's get started. So arrays, they're great data, runtime data stores, right? You can put all sorts of things into them, strings, coordinates, whatever you want. But they do have some limitations. Say I needed to search for a value to replace in an array. The longer the array, the harder this becomes. In order to do this replace, I have to transverse this array looking for that particular match. In computer science, this is called an O of N algorithm, which is one of the slowest algorithms that you can use on a search. So this means I would have to do a computation for each one of these slots over and over until I found the match that I was looking for. When you get more slots, you can imagine how this doesn't scale very well. It gets really slow pretty quick. So we enter a hash table. A hash table allows you to search and store things like an array, but it magically knows where your desired record is. Like an array, a hash table can store strings, coordinates, numbers, integers, pretty much anything you want to throw into it. There are millions of ways to use the hash tables. Most programming languages provide a hash table that developers use almost every day. In Python, you've got dictionaries. In Ruby, you've got a hash. In PHP, you've got associative arrays. Java's got hash maps, so forth and so forth. Some great uses of a hash table: handling command line arguments, storing web form data, storing HTTP headers, storing session data, counting how many of each, removing redundant copies of data, speeding up lookups of an existing array, so forth and so forth. And Jason Orendorff literally could write out 1 million of these if you didn't stop him. So all over the place. So now that we have an idea what generally a hash table is and when's a good time to use it, we're going to dive into and see what actually makes up a hash table. And a hash table is pretty simple. It's your data store, i.e. your array, wrapped around with an interface. So it's wrapped around this set of methods, your interface, which varies based on the application but has the same basic requirements. The first two basic requirements is an add method, so you can store things add things to your data store, and then a lookup method. But the critical thing is the hash method, and this is your private method you don't want anybody messing with that makes your hash table a hash table. This is the method that's used to locate where to store and where to grab data from. The hash method takes a key, performs a secret hashing sauce, and returns a position in the data store to add and find the record. As simple as that. There's many strategies for creating a hash method. Which is best depends on your actual situation and the application you're trying to build. But still, the structure allows you to handle dynamic scaling of your data store, rehashing as needed, and establish collision management as your project requires. Collisions is something important to plan for and something that you should always count on happening. Collision is when two different keys put through the same hash method end up with the same data store index. Collisions are always possible. Once you have one collision, the likelihood of a second collision goes up and increases. And the more collisions you have, the more likely you're going to have more collisions. So you need to plan for collisions. There are two main ways to handle collisions in a hash table. The first is through linear probing, adding more slots. Expanding slots requires rehashing of the indexes, which can take time. And as more slots are added, it starts to negatively impact performance. So you start getting into that O of N issue where you have 10,000 records you have to go through. The other collision handling strategy is a linked list. The linked list chains together keys which resulted in a collision into the same index. The idea is that the linking will significantly reduce the need to search by limiting the number of slots that need to be searched by the way of the hash index. So basically, your hash will tell you that will get you the first half of the way to your data, your value that you want to return. So your hash will always return one index, and then you know that all you have to do is search through the linked list to find your value. This is a O of end over K, which in theory is the same of O of n, but in practice is significantly better for searching. And then I got one more thing for you. For people who are in the object-oriented programming world, this is a hash table in structure. You've got a hash table, you've got your data store, which is your table of arrays, and then you've got three methods that are required at the base. You can expand beyond that. You've got your lookup, which requires a key, returns your struct. You've got your add, which requires a t, your key and some values. And then you got your hash, which returns the position in the table. So that's what I got for you. Any questions? Awesome. Told you it would be easy.